Hey everybody, Mr. Jones here. Today we're going to talk about the three main states of matter: solids, liquids, and gases. We're going to use dry ice to do a couple experiments so we can see some phase changes and we can see some real science going on. But before we get to that, I want to refresh your thoughts on a few things. So let's think about solids. Solids, like ice or snow, have low energy and very little particle movement. The particles inside a solid are packed super close together. They just vibrate in place. And because of that, a solid, like an ice cube, will hold its shape and volume. If we add energy to an ice cube, it changes or phase changes from a solid to a liquid. And if we think about the particles inside of a liquid, they have medium energy. They're still really packed tight close, but they've got enough energy that particles in water can slide past each other. And it's that sliding action that allows a liquid to hold its volume. The volume stays the same, but a liquid doesn't hold its shape like ice. A liquid, obviously, if we pour it out, will take the shape of a container or spill all over. If we add even more energy to this water, the particles speed up more and get faster and faster, and they spread out even further until they turn into a gas, much like fog. Gas particles have a very high energy and they move about freely. Huge amount of space in between them, and because of that, there aren't bonds strong enough to hold gas particles close together. So gas particles are all around. They don't hold their shape, they don't hold their volume, they go wherever they want. So we've got solids, liquids, and gases all around us. We're going to talk about those phase changes. What really happens when we go from a solid to a liquid or a liquid to a gas? So let's remember this. Looking at the particles inside of a solid, liquid, or a gas, if we add thermal energy to those particles, so here we've got particles. If we add thermal energy, these particles start to shake more and more. If you add lots and lots of thermal energy or more and more heat, these particles, the bonds in a solid, like this ice cube, the bonds are held together, they're pretty strong, they're vibrating in place. As you add more energy, those bonds break and it turns into a liquid, and those liquids, they can move about themselves and slide past each other. If we keep adding that thermal energy or that heat, these bonds will break and the particles will zoom around all over the place like a gas. The energy we're talking about is thermal energy or heat. The more heat you add, the faster the particles move. The faster they move, the further they spread apart. The further they spread apart, the more their bonds break, and you go from a solid holding its shape and volume to a liquid that can only hold its volume, to a gas that holds neither its volume or shape and just zooms all around. Now, the process in which a solid turns into a liquid or a liquid into a gas is called phase changing. Now, let's think about it. If we go for a solid and we add energy or we add heat, so think about ice. If we add heat to ice, what happens to the ice? It melts. Melting is that phase change. And that phase change turns that solid into a liquid. Think about it backwards. If you have a liquid and you take away energy or you make it cold until it turns into a solid or ice, what do we call that? Right, freezing. Liquid to a solid, freezing. Solid to a liquid, melting. And then think about liquid to a gas. If I boil this, or the water all leaves and turns into gas, what do we call that? Evaporation. Just like when it rains, the water from the water puddles evaporates. It phase changes from a liquid into a gas. So these particles warm up, speed increases, distance increases until they phase change into a gas. We call that evaporation. Think about fog or rain clouds. You've got all these gas particles up. Once they start cooling down and they slow down and they turn from gas into liquid, they fall out of the sky. We call that condensation. Think about cracking open a cold soda on a hot summer day and the outside of the can gets wet. That's because you're taking those hot supercharged air particles in the air and they're cooling down against your can, and they're condensating, or they're turning back from a gas into a liquid. So keep those thoughts in mind when we go through this dry ice. Now for water, our freezing point or our melting point, it's the same thing because it either goes from a liquid freezes to a solid or a solid liquefies into a liquid. The freezing or the melting point for water is 0 degrees Celsius. The boiling point or the evaporation point or condensation point for water is 100. That means any particles of water that are above 100 degrees are always gas. Any particles of water that are between 0 and 100 are liquid. And any particles of water that are below 0 are solid because they're frozen. We're going to use dry ice. Now, dry ice is interesting because dry ice doesn't condensate or evaporate. It doesn't really melt. Dry ice skips a liquid phase. Dry ice goes directly from a solid to a gas. We call that process sublimation. So keep that in mind. We're going to need it later. So we're going to be using dry ice today. Now, safety first. Before we do any experiments or anything, you've always got to have safety. For dry ice, even though you can buy it in a supermarket, it's still kind of dangerous. You definitely need a glove. Dry ice is so cold that if this was a dry ice cube and you held it in your hand, it would freeze the blood cells in your hand. It's that cold. So you got to wear a glove because you don't want to burn your skin. Also, make sure you've got safety goggles or glasses on because you don't want stuff to splash in your eye. If you got a piece of dry ice in your eye, it would freeze your eyeball. That wouldn't be good. So always make sure safety first. I've done a lot of stuff with dry ice, so I'm pretty comfortable. I got my gloves. I got my glasses. We're ready to go. Now, I got some dry ice right here. Remember, this piece of dry ice, hammer of science, it's a solid. Can you see the gas or the smoke coming off of it? It's sublimating. It's going through sublimation. This solid is turning directly into a gas. There's no water dripping down. It's sublimating. It skips the liquid phase. Now, the reason dry ice sublimates has to do with the temperature and the energy inside of dry ice. So, dry ice sublimates or freezes at minus 109.3 degrees Fahrenheit or 78.5 degrees Celsius. That is wicked cold. It's pure carbon dioxide. And it's carbon dioxide gas that's been pressurized and made so cold, 109.3 degrees below zero, that it's a solid. Carbon dioxide in its natural form is a gas. It wants to be a gas at room temperature. Inside the classroom here, it's probably 70 degrees. This dry ice is minus 109 degrees, which means it's almost 180 degrees colder than the air around it. Because of that huge temperature change, the particles inside this dry ice that are really held tight together and just vibrating in place, they go from 109.3 degrees to instantly touching something that's 70 degrees, and that instant change doesn't allow them to slide past each other by turning into a liquid. It breaks those bonds instantly and goes from a solid instantly to a gas. That break, where it skips the liquid phase, is called sublimation. Dry ice is one of the very few things that we can buy and we can mess with and we can experiment with that sublimates. So, we are going to use this today. We're going to learn a ton from it. First things first, though, let's work this out. We've talked about atoms and we've talked about elements. We've talked about subatomic particles, protons, neutrons, and electrons. We've talked about electron clouds and why elements need to be balanced and happy. And they want 8 electrons in their outer shell. So remember, this is frozen carbon dioxide, or CO2. So it's made out of carbon, the 6th element on the periodic table, which you know then it's got 6 protons and 6 electrons. So it's made out of carbon, C, and then it's made out of O2, or 2 oxygens. So you have CO2. You got a carbon, an oxygen, and an oxygen. CO2. Using your knowledge of how the atoms look. Carbon, 6 protons, 6 neutrons, 6 electrons. 2 in the outer shell, 2 in the inner shell, 4 in the outer shell. Remember, carbon wants 8 in its outer shell to be balanced. Hey, here we have oxygen. Look at oxygen. 8 protons, 8 neutrons, 8 electrons. 2 in the inner shell, 6 in the outer shell. Oxygen wants 2 more to be happy. You have CO2. Carbon needs 4 electrons. Each oxygen needs 2 electrons. This oxygen will share 2 electrons with this carbon. The other oxygen will share 2 electrons with this carbon. Carbon gets 4 electrons from the oxygens. Each oxygen gets 2 electrons from the carbon. You're going to want to draw this chemical compound. Draw it like this. Use these diagrams. You'll have carbon, and then you're going to have 2 oxygens. Draw them together, show the electrons being shared, make each one of them have 8 in its outer shell. Draw also how the particles inside this CO2 look. In other words, what do the particles inside this solid look like? They look like every other solid, but what do solid particles look like? This is your first set of questions you must answer, so I'll let you answer those now. All right, now that you've done that, we're going to make Washington wiggle. In other words, we're going to make George Washington, the man on the American quarter, we're going to make him dance. And we're going to make him dance by making his particles as cold as these particles. So let's first think in terms of particles, energy, speed, and spacing for both the dry ice and the quarter. Both are solids. So when you draw the particles of a quarter, you draw the particles of the dry ice, they're both solids. They're both going to be tightly packed in there, vibrating in place. But this quarter is about 70 degrees. This dry ice is 109 below zero. So when these warm particles touch the super cold particles of the dry ice, remember the dry ice sublimates, or it boils, it phase changes at minus 109. The quarter is a lot warmer than that. So we can't see these particles. But what's going to happen is, inside the dry ice, those particles are moving, they're pretty slow. Inside the quarter, the particles are moving, they're slow, but the quarter's a lot warmer. When these particles from the quarter touch the super cold particles of the dry ice, they warm these particles up so fast that they break those bonds. In the process of breaking those bonds, we can see it because we can watch this quarter as we put it in dry ice. We can watch this quarter move around. So let's check this out. We've got our dry ice here. If you're quiet, you can hear the particles smashing into the quarter before it starts to move. So I don't know if you could hear that, but that's the sound of the particles. Now let's watch Washington wiggle. I don't know if you can see. I'll try to zoom it in on this camera. You can see how it's moving for sure. It's moving because of the particles. Think about the particle speed. Think about what the particles inside this quarter must be doing when they come in contact with the super cold particles inside of the dry ice. So, Think now, because you're going to answer this. Think in terms of the particles and energy inside this quarter, the solid particles. Think about the particles and energy inside the dry ice, these solid particles. When they collide, even though we cannot see these particles, when they collide, when these warmer solid particles from the quarter touch the cold solid particles of the dry ice, that quarter makes them sublimate. It switches them. So those particles, although we can't see them, we can see that they're moving and breaking apart because they force this quarter to move. I'll show you again how that happens. So if you look, we got our dry ice right here. I'll put our quarter in. You can see it sublimating a little bit. Now watch. See him wiggling? He is wiggling because even though we can't see those particles, they're inside those solids. We are phase changing the particles inside the dry ice directly into a gas. And as those particles escape, they're slapping that quarter. And they're moving right past the quarter and they're bouncing off into the air. So those solid particles, even though we can't see them, they're smashing into the quarter so you know those particles exist. So now, answer this question. What causes Washington to dance? Why is he wiggling? Why is he bouncing like that? Think in terms of particles. Answer this question now. Now, we made Washington wiggle, but we can also make Washington sing or scream. Because when we put the quarter vertically in the dry ice, we're only getting the particles on the very outside of this quarter. So the particles only have a very thin area to bounce off of. If we take Washington and we slap him face down in the dry ice so that all these particles are meeting these particles, they can't escape as easy. They can't smack into the quarter and make it bounce. So they literally have to squeeze past it, almost like fingernails on a chalkboard where it would screech. So think about this. We're going to make George Washington scream. What causes these particles to scream? Think about speed, think about spacing, think about where they're going. Where are the particles from this dry ice going when this quarter sublimates them or phase changes them from solid to gas? And then as they try to escape, listen to them make George scream. Are you ready? So, it's a pretty quick sound. But I'll do it again, and I'll do it in the camera so you can see it. When we push that in, now I don't think you can probably see, but if the lighting was right, you can almost see the indentation right here on the dry ice. When the light hits it correctly, you can actually see the face of the quarter in there because it has pressed in and those particles have melted themselves in. You can actually read it in the ice where it says United States of America, and you can even say where it says $quarter. So listen again. I'm just going to take this dry ice, these particles that are 109 degrees below zero, and they're going to smash into these warm 70-degree particles, and these are going to try to escape, but they've got to scrape past this. So you're going to describe this. Think in terms of the particles. Why does this scream? Ready? One more time. Now, it only also screams until the quarter gets as cold as the dry ice. Because once the quarter's particles are that cold, they don't really move as much. So, think about that. Now, answer that question. What caused the quarter particles to scream against the dry ice? First, you're going to draw what these liquid water particles look like. Second, you're going to draw what the solid dry ice particles look like before sublimation. After I break this up, I'm going to put it inside of our jar of water, and you're going to watch what happens. while the experiment is going on. Illustrate the dry ice particles after they sublimate. After something starts happening, draw what they look like. Then in your own words, explain what's happening to the particles as this dry ice sublimates and turns from a solid to a gas. Always remember to include particle speed, spacing, and your energy. So I'm going to take this and I'm just going to break it into some smaller pieces. So I can, there we go. I've got some smaller pieces now. I'm going to drop them in our water. Watch what happens. They go right in there. They instantly start to sublimate. So if you listen, you can hear them. So you can see inside you have liquid water surrounding the solid dry ice. That dry ice is now boiling because the water is so hot compared to minus 109 degrees. So you drew the liquid particles, you drew the solid particles. Now it's sublimating. What about these particles? What are the particles that are spilling out? This pure carbon dioxide gas. Illustrate those particles. Once you've illustrated the gas particles, then in your own words, explain what's going on in terms of particles, spacing and speed. What is going on inside this jar as this dry ice sublimates? What's happening during this process of phase change? So make sure you draw those. Now for our last experiment, I decided what I would do with this is prove to you, using dry ice, water, and some balloons, that gases have masses. So check this out. I realize it's hard to understand that gases have masses unless you can measure the mass of a gas. So we're going to use some balloons in a bottle, some dry ice and some water. Now you're going to see that gases have masses even if you forgot your glasses, because I'm going to prove it to you using science. So check it out. You're going to see why gases have masses. I have two balloons. These balloons weigh or have the same mass. Here we are. I've got a balance. It's not a triple beam balance. It's just a simple one, but it works because if we look, we let it stop moving, it's balanced. I have two red balloons. This red balloon and this red balloon. If I put them both in and it stops moving, they're balanced. They're the same balloons out of the same bag, 12 inches in size, both red. They weigh the same amount. One balloon I'm going to blow up with my mouth. So that balloon I'm going to draw a smiley face on. It's going to become my balloon that I blow up. So I'll put a smiley face on it, and we know which one that is. So here's the balloon I'm going to blow up. Smiley face balloon. Here is the balloon our dry ice is going to blow up, and I'm going to call it CO2 because that's what dry ice is. So this is our CO2 balloon. Our CO2 balloon. So we've got two balloons that weigh the same mass. Those balloons don't have gases, so we're not measuring the masses of the gases yet. We're just measuring the masses of the balloons. Before we measure the masses of the gases, we must know a few things. For example, the gases that we exhale when we blow up a balloon, those gases are made up of about 78% nitrogen, 16% oxygen, 4% carbon dioxide, 0.9% argon, and then the remaining stuff is just other trace gases. When our balloon gets blown up by the dry ice, it is 100% pure carbon dioxide. So, one balloon is going to have pure carbon dioxide, only CO2. The other balloon, the one that we blew up, is going to have nitrogen, oxygen, CO2, and some other stuff. I'm going to blow them up to have approximately the same amount of volume. So, Before we do this, you're going to observe this experiment. After we're done, you're going to use your knowledge of the particles, particle spacing, volume, and mass to describe what the particles in each of these balloons must look like. Because it's going to look different when we're done. And then, how does this experiment prove that gas is matter? So first off, let's get a water bottle of science. Here we got a water bottle. I'm going to put a little bit of water in there. Here we go. We got some water in there. Now, I'm going to break up small pieces of dry ice so I can fit it inside this bottle. So I'm going to put on my safety glove again. I'm going to reach down into the cooler of dry ice. There are some smaller pieces, so I'm going to break them up first. So we've got some smaller pieces of dry ice here on the table now. I'm going to use these particles of these chunks of dry ice that are down here. I'm going to break them into pieces big enough to put in this water bottle so that we can use the water bottle to blow up the balloon. Right now, I'm just breaking some smaller pieces of dry ice up so that we can get it into the balloon and make this balloon sublimate and we can get the balloon blown up. So step 1, I got my water. Step 2, I got my dry ice. Step 3, here goes the dry ice into the bottle. All right, now our bottle's really going. We got plenty of dry ice in it, so you can see it's going to blow this balloon up fast. So what I'm going to do is I'm going to put the balloon on, and I'm going to hold it. Now, here comes our CO2 balloon. It's being blown up by the process of sublimation. So I'll let it get nice and big, and then I'll blow up the other balloon to match the size and volume. So let's get this thing blown up. Let's call this good. So we'll let the bottle go back there and keep bubbling, and I'm going to tie this balloon off. So here is the balloon. It's tied off. This is our CO2 balloon. There's our CO2 balloon. Now I'm going to blow up this balloon, hopefully about the exact same size. I think that's about the same size. It kind of looks like it from here. So I'm going to tie up this balloon. Now remember, this is the balloon I blew up. So this balloon contains nitrogen, oxygen, carbon dioxide, argon, and other things. This balloon contains carbon dioxide from the dry ice. As you watch what happens, carbon dioxide, argon, nitrogen, oxygen. These gases have masses. Which gas has the most mass? This gas has one compound in it, CO2. This gas has got a bunch of different compounds. That might not mean anything, because watch what happens when we mass this gas. Are they even? Let's put them this way. Are they even? Face CO2. Which one's heavier? Check it out. Well, they're going to fall out. I'm going to put them this way. Look there. The CO2 balloon is significantly heavier. CO2 balloon has more mass than the face balloon. Remember, we massed these before I blew them up. They were the same. Look, there's our balance. Our balance is balanced again, but if we put the CO2 in the one we blew up, obviously, look, even if we push down the one that we blew up, CO2 always wins. The gases have masses. So, now think about it. What must the particles look like inside this balloon compared to this balloon? They got the same volume, but these particles have more mass. Why is that? Hopefully, this experiment got you thinking more and more about phase changes, particle size, and particle spacing. Be sure to go through each question, answer them as best you can. Pause when you need to. Feel free to send me any questions if you ever have anything you're wondering about. I hope this helped. I hope you enjoyed it. Have a great day.